Well, hello, good morning, good afternoon, and good evening, everyone, and welcome to the second session of the Scientist.com AI Innovation Series. My name is Chris Peterson. I'm the co-founder and CTO here at Scientist.com. Last time, we talked about neural networks, what they are, and how they're trained. We even went deep into the math to show exactly how that's done. This time, we're going to build on that knowledge to discuss embeddings, which are also known as word vectors. We're going to talk about what they are, how they're trained, why they're foundational to natural language processing and large language models. Okay, so as I mentioned, this is part 2 of our series on how large language models work. We did talk about neural networks last time. Today, we're going to talk about embeddings. Last time was very heavy on the math. We went deep into the matrix, the linear algebra, the matrix multiplication, as well as the calculus. This is going to be more conceptual. We're going to coast a little bit on the math we did last time and talk about how we use that to train embeddings. But don't worry, we are going to get back to the math in part 3 when we talk about attention. So what is an embedding? Well, embeddings convert words into high-dimensional vectors that retain meaning. Right? So what does that mean? Well, I'm showing a couple of vectors here to the right. These are low-dimensional. These are just 3-dimensional vectors because it's easier to talk about in low dimensions, or it's easier to display. What happens is when you create an embedding or we create a word vector, words that are similar in meaning appear close in meaning space. So we have antibody and peptide up here. Those are related words. They're going to be, not the same, but they're going to be in a similar part of meaning space. And we've got a different vector down here. Boxing is just completely different. I've heard boxing referred to as the sweet science. I think that's a different type of science than we're talking about up here. Embeddings are usually much higher dimensionality than this. Some of them are hundreds of dimensions. The one we use here is 768 dimensions. Oftentimes, there will be many thousands or even tens of thousands of dimensions. I've seen embeddings that use 16,000 dimensions to embed, that they embed words in. So what can you do with these? Well, it's more than the fact that similar words are in similar part of meaning space. The relationship between words is also retained. So this is one of the canonical examples here. So if we take the vector for man and the vector for woman, and we look at the offset between those two vectors, that offset is going to be very similar to the offset between the vector for king and the vector for queen. So that sort of male-female relationship between these two vectors is retained. The same goes for verb tense. So we have inspecting and inspected. The offset between those two vectors is going to be very similar to the offset between researching and researched. And this is another very popular example that you'll see on the internet. This is a country capital. So the sort of capitalness of a word is that meaning is retained. So the difference between Ottawa and Canada is going to be very similar to the difference between Madrid and Spain, which is similar to London to England, and Paris to France, et cetera, et cetera. These are just 3 examples. The idea of an embedding is as much of the meaning of the word as possible is going to be embedded, encoded into this meaning space so that the relationships between words are preserved in this in these vectors. And just to drive that home, you can perform vector math on these vectors, and that's going to be meaningful linguistically. All right. So if you think back to your SATs and you had those analogy questions, right? Man is to king as woman is to blank, or England is to London as France is to blank. We can now formally define those using vector math. So if you were to say man is to king as woman is to blank, you can turn that into an actual equation using vector math. You can take the vector for king, subtract out man, you can add the vector for woman, and that's going to put you at a point in meaning space that is very close to the vector for queen. You can do the same thing here. London minus England plus France is going to put you at a place in meaning space that is very close to the vector for Paris. I don't know about you, but I think that is super cool. When I first read about word vectors, it kind of seemed like magic, and I kind of had to know how they work. So I said we were going to talk about what embeddings are. So far, I've kind of just told you what they can do. So what is an embedding? Well, I asked ChatGPT for a definition, and this is what it gave me. Word embeddings are numerical representations of words derived as the input to hidden layer weights in a single layer neural network, which capture linguistic patterns by learning from the context of word usage. Simple, easy enough to understand, presentation over. Obviously, that's kind of a mouthful, so let's break it down. Word embeddings are numerical representations of words. That's the vector part. They're lists of numbers. They are derived as the input to hidden layer weights. We know what the input to hidden layer weights are based on our last talk, right? Those are the weights that connect the input layer to the hidden layer in our single layer neural network, which we talked about last time, which captures linguistic patterns by learning. That's the back propagation from the context of word usage. And frankly, that's what we're going to spend most of our time on today. But first, let's do 2 quick slides to review the neural network stuff that we talked about. So if you recall, we trained a network to play tic-tac-toe. We just gave it one example, and we looked at how it learned that one example, but that was the gist of it. And the first thing we had to do was we had to encode our tic-tac-toe board as a list of numbers, because neural networks don't understand tic-tac-toe. They don't understand words. They don't understand images. They only understand lists of numbers. So we have to encode tic-tac-toe as a list of numbers. We had an input. In this case, it was 1 followed by 8 zeros. And we had an expected output. In this case, it was 4 zeros, 1, and then 4 zeros. And we fed the data forward, and then we used back propagation to adjust the weights. And you will recall that using all the math that we did last time, that I'm not going to rehash here, through the math of back propagation, that caused some of these weights to strengthen and some of these weights to diminish, all with the goal that when you get a 1 here, you output a 1 here. That was the goal of the network, and the training increased the weights of some of these edges and decreased the weights of others. So that was what we did last time. That was our neural network to play tic-tac-toe. This time, we're going to create a neural network, a much bigger neural network. It's still going to be a single layer, but it's going to have a lot more nodes in it. And the idea is we're going to train a neural network so that we give it a target word, and we are going to attempt to predict the words that appear in context with that word. And if that doesn't make sense, don't worry, because we're going to go into a lot of detail about what that means. This is what's called a skipgram model. It's used by a program called Word2Vec. That was one of the first programs that I encountered word vectors in. There are other models. Some of them sort of flip it on its head and kind of flip everything that we're going to do back, and do it backwards. But conceptually, it's very similar. So we're going to focus on a skipgram model. So we're going to take a target word. We're going to try to predict words in context. Just know that there are other models to compute embeddings. They are very similar to this, conceptually anyway. So here's our agenda. It's very similar to when we trained our network for tic-tac-toe. We have to encode our training set. We have to decide on the structure of our network, and some of that is defined by our training set. We're going to train our network, and then we're going to talk about some of the practical uses for the embeddings that result from it. So first, let's encode the training set. So what you're going to start out with is a big corpus of text, just as much text as you can get your hands on, right? And I've been talking about words, and I'm going to continue talking about words, but know that what this actually works on is tokens, and there are different tokenization strategies. Sometimes it'll work on subwords. Sometimes it'll work on groups of letters. I'm going to continue focusing on words because that's how most of them work. And it's definitely the easiest to sort of to think about and to explain. The other thing that you need to, when you're tokenizing your text, that you need to think about is punctuation. So when you're tokenizing, essentially you're taking a bunch of text and you're breaking it down into individual words or subwords. What do you do with the punctuation? For this example, I'm going to ignore it. I'm going to treat it like it's not there. If you were actually training an embedding algorithm, that wouldn't be a great strategy. A lot of the more robust ones, use punctuation as part of the tokens or tokenize them separately. If you were going to use this embedding, for instance, in a code-based environment, a lot of code includes parentheses and curly braces and square braces and all sorts of punctuation. You obviously would have to deal with it. Again, for example purposes, I'm going to treat it like it's not there. But just know if you were doing this for real, there are different tokenization strategies, and you have to deal with punctuation. Okay, so the next step, now that you've taken your big corpus of text, bunch of text, all the text you can find, and you've broken it down into individual tokens or words, the next step is to create a vocabulary. So in your corpus of text, you might have 10 million words. There might be 100 million words, whatever it is. In there's some set of unique words or unique tokens. Maybe it's 500,000 unique words that appear in your corpus. That's your vocabulary. So your vocabulary is going to be of size, in this example, 500,000. And what you're going to do is you're going to line them up. I'm going to say alphabetically. Maybe your first token in your vocabulary is alpha, and the last token in your vocabulary is Z. And what you're going to do is at each position, you're going to put a 0. But for the word that you're encoding, you're going to make that a 1. So when you encode alpha, that's the first word in your vocabulary. It's going to be encoded as 1, followed by 499,999 zeros. Z is the last word in your vocabulary. It's going to be 499,999 zeros, followed by a single 1. Right? And somewhere in the middle, you're going to have queen, and it's going to be a bunch of zeros until you get to the position for queen. That's going to be a 1, and then you're going to have a bunch of zeros after that. Pardon me. And what you're left with is a list of 500,000 encoded words. Each word is a list of 500,000 numbers, all of which are 0, except for a single position, which is 1 in each one. And that's going to look something like this. It's a big, this is going to extend north, south, east, and west. It's going to be 500,000 by 500,000 integers. They're going to all be 0, except for this line right down the middle. And that's how you're going to encode each word. So whenever I use the word queen, it's really going to be, this big long list of zeros, 1, and then another big long list of zeros. It's an array of 500,000 integers. Okay, so that's how we encode each word. How do we create the context? So this is a little bit of a naive way of doing it. There are other ways of picking words in context. But let's just pick on this sentence here. The queen and her daughter, the princess, lived in the palace. I'm going to use a context window of size 5. What that means is, for every word in this sentence, I'm going to treat each word as a target word. For each target word, I'm going to look forward 5 places and backward 5 places. So for the word the, this is my target word. The context words are queen and her daughter, the. For the target word queen, I look forward and backwards. So my context is the and her daughter, the princess. Target word and, context, the queen and her daughter, the princess, lived. So on and so forth. And each pair is going to be one example that I'm going to feed to my network. So the queen, the and, the her, right? Daughter, queen, daughter, princess. Like each one of these is going to be a single example. And as you can tell, there's going to be a lot of examples. There's 5 in this line, 6 in this line, 7. There's going to be 80 examples total for this one sentence. So you can imagine when you have a large corpus of text, you're going to have a lot of training examples to train your network on. Okay, so what that training data is going to look something like this. So I'm picking on the word princess here. For princess, you're going to have 9 words in context, and your training set is going to be, for these 9, princess is always the target word. This is going to be the input to your network. But the expected output is going to vary. So it's going to be, we're going to train it for queen, we're going to train it for and, we're going to train it for her, etc., etc. And we're going to do that for every example in our training set. So I thought this is a good time for an aside. Last time we talked, there was a question about supervised versus unsupervised learning. What we're looking at here is unsupervised learning. Supervised learning requires labeled data. So imagine we were training a neural network to recognize cat pictures on the internet. Somebody, someone, or something would have to label a bunch of pictures to say whether or not they included a cat, right? And that would be an example of supervised learning. That would be an external system, external to the system that we're training, actually labeling that data so that the system could learn from it. That's supervised learning. What we're doing is unsupervised learning. There's no labeling involved. What we're looking at, we're developing our training data from the actual structure of the data that we're looking at. Nobody has to label explicitly the and princess. They just appear in context. So this is unsupervised learning. That was a good question from last time. I just wanted to make sure we addressed it again. Okay, so that is how we develop our training set. Now let's look at the structure of our network. And if you recall last time when we trained it to play tic-tac-toe, some of this was dictated by the structure of our data. When we're playing tic-tac-toe, the inputs are always 9, and the outputs are always 9, because that's how many places we have to move. Here, our inputs are always going to be a word encoded as a series of numbers that are of size vocabulary. So our input layer size has to be the same size as our vocabulary. Likewise, we're trying to predict how likely each one of those words are to appear in context, which means the output size has to be of size vocabulary as well. So those two are fixed just based on the structure of our training data. The hidden layer size, here's where we get to make some decisions. Like I said at the top, some embeddings result in 768 dimensions, some result in 1024, some result in thousands of dimensions. Whatever the dimensionality that you're looking for in your ultimate embedding, that's the size of your hidden layer. We'll see why in a minute. But if your resulting embedding has 768 dimensions, pardon me, then your hidden layer is going to have 768 nodes. We're going to keep it simple and use a linear activation function for our hidden layer activation function. And then for our output layer activation function, we're going to use softmax, and our loss function is going to be cross entropy. You will recall these are the same functions we used for tic-tac-toe. Softmax essentially creates a probability distribution, but it's a probability distribution that deals nicely with negative numbers and with zeros. And cross entropy is a loss function that compares two probability distributions. And what we're looking to do is predict the likelihood that each of the words in our vocabulary will appear in context with our target word. That is essentially a classification problem, very similar to our tic-tac-toe problem. So softmax and cross entropy make a lot of sense here. Okay, so we've got our training data and we've structured our network. Let's go ahead and train it. Like I said, we're going to skip over the math. We're going to coast on the math we did last time. Just know that it is exactly the same thing that we did last time. We're just feeding it different training data, but essentially it's just longer numbers of zeros and ones, but it is exactly what we did last time. So I'm going to take you through a couple of individual pairs of words. So what we're looking at here is princess and palace. Just those two words. It comes from this sentence: the queen and her daughter, the princess lived in the palace. But we're feeding in princess and we're expecting palace out, which means all zeros until you get to the position for princess, which will be a 1, and then all zeros, and likewise for palace. So you'll feed that through. The first time through, it'll be randomly initialized. You'll get random numbers, and it will back propagate to some of the nodes to strengthen the connections between those nodes, so that when you get a 1 here, you're more likely to get a 1 here. This is the back propagation that we worked on last time. So in this case, it's going to strengthen these weights, and it's going to diminish other weights. And remember, this is only a small portion of the network. There's going to be hundreds of nodes here, and thousands or tens of thousands of nodes on either side. So that's one example, princess to palace. It used these 2 nodes. Now we're going to say queen and daughter. So once again, this is a 1 at the position of queen. Everything else is going to be zeros. 1, and we're expecting a 1 at the position of daughter, and everything else to be zeros. This time, it's going to use somewhat different nodes. It's going to use this node over here, and it's going to strengthen the weights here, and it's going to use this node here. So it's reusing one of the nodes that princess used to get at palace, but it's also using a node here that princess wasn't heavily relying on to get to palace. And remember, we have far fewer nodes in our hidden layer than we have in our input or our output layer. So it is going to have to reuse nodes in the hidden layer. In fact, that's kind of the point of what we're doing. So it's going to reuse this node, and it's kind of using this node over here that princess and palace didn't really rely on. Okay, next word. Now we've got queen and palace. It was a palace fit for a queen. So again, just the word queen, just the word palace. Now we're looking for a 1 here. And the network, through back propagation, because of the linear algebra and the calculus we talked about last time, is going to realize, I'm anthropomorphizing the network already, but it's going to, the math is going to point to reusing these nodes, because if it wants to get a 1 here, it realizes that's the same as when princess wanted to get a 1 here. So it's going to reuse these weights. To do that, it's going to strengthen the weights here, which is going to basically conceptually draw queen closer to these nodes than it is to other nodes. Okay, now for something completely different. Apple trees are common in New England. The word apple and the word tree, it's going to go way over here, and it's going to use some node that is unrelated to queen and princess and daughter and palace, and to get at tree. And then it's also going to use a little bit of this one, which is one of the nodes that the queen and princess used to get at palace. Then we have apple and salad. Rachel loves apple in her fruit salad. It's going to use this same node over here, but it's going to use less of this one, and the back propagation is going to strengthen these nodes over here. And finally, the last example, parrots commonly nest in dipteris trees, which is actually true. I learned that for this presentation. And when you back propagate, tree to parrot, it's going to go through this node here, which is a node that we've used basically every time. And remember, this is all happening in the same network. So after you run this through with all of your other examples, you're going to end up with a series of weights. And these weights are going to be tuned to minimize the loss function, right? So these weights are going to be tuned to make the network maximally accurate at predicting the words that will appear in context with your input words, right? And in doing so, it's uncovering the structure of the language, right? There are rules that govern the language. It is encoding those rules into the network the same way that it encoded the rules for tic-tac-toe into the network. It's just a much bigger network with a lot more rules, right? And it has to reuse these nodes just by necessity. There's just a far fewer hidden nodes than there are input and output nodes. So it has to reuse them. And it conceptually, the higher the weight here, the more closely related an input node is to a hidden node. Now here, I'm really going to anthropomorphize this pile of linear algebra. And I'm going to say what these hidden nodes are conceptually are concepts in our language, right? So the network is uncovering the latent structure of the language, right? It is encoding the rules of the language into this network because that's the only way to minimize the loss function to most accurately predict the words that will appear in context. You have to encode the meaning, right? Like if words were just random, none of this would work. But since words appear in an order that has meaning, that meaning is then being transferred into here. And one way to conceptualize that is to assign concepts to these nodes, right? So we see that this node helps connect queen and princess to palace. That could be a node that's associated with royalty, right? We have a node here that helps join princess and queen to daughter. That could be a female node, right? It would make a lot more sense if we had more examples. This node here helps connect not only queen and princess to palace, which is where they live, but also apple to tree and parrot to tree, because that's where the apple comes from and that's where the parrot nests. This could be something like home or comes from. And finally, we've got some node over here that connects apple to salad, and this could be some sort of like fruit node, some sort of fruitiness node. This is like a naive way of interpreting it. There's no reason to think in word2vec there is a single node in the neural network that corresponds to royalty. But royalty is encoded in the network somehow. It's probably some combination of like 2 or 3 or 10 nodes. But royalty, this concept of royalty is essentially the offset between woman and queen. It is that offset between man and king. I'm explaining it here as if it was a single node, but it could be, and it likely is, a combination of multiple nodes. So if we think back to the beginning, we're not actually interested in predicting words in context. What we're interested in is creating embeddings. So we can actually throw the second half of this network away. We're not even going to use it. It was a means to an end. And what we're left with is the input to hidden node weights from our definition, right? And this is how closely connected each word in our vocabulary is to each node in our hidden layer. Or put another way, how tightly coupled each word in our vocabulary is to each concept that our network is encoding. So if you were to just look at these 4 words with these 4 nodes, you would end up with embeddings of 4 dimensions or 4 numbers. So you would have a number that links queen to female, queen to royalty, queen to home, and queen to fruit for whatever reason. And likewise for the other words. So let's look at another example. So I'm not going to go through the training of this one, but let's imagine a network. And we have England, London, Paris, and France as our input words. We have 4 nodes that we're showing anyway in our hidden layer. One node is going to relate to Englishness. One is going to relate to capitalness, Frenchness, and placeness, right? England and London are going to end up more closely coupled to the node that represents Englishness. And once again, this is a naive way of talking about it. It could be multiple nodes. But because England and London are going to appear in context with other words that are English more often, they're going to end up with stronger connections to that node. London and Paris are going to appear in the context of capital cities more than England and France. So they're going to be more tightly coupled to capitalness than England or France will be. Obviously, Paris and France are more French than London and England. So they're going to be more tightly coupled here. Once again, only because they appear in context with other words that are associated with being French. And finally, all four of these are places, and they're going to be used in context as places. So they're all going to be roughly equally tied to the placeness concept here. So if I turn these into numbers, I'm not going to read all of these out, but you can just visually see here. London is tightly coupled to Englishness. So is England, right? England and France are not tightly coupled to capitalness, but London and Paris are, et cetera, et cetera. So now we can perform our math. So we have England is to London as France is to blank. We're going to turn that into our equation. London minus England plus France equals blank. So let's do the first step here. London minus England. So 0.75 minus 0.8, going to give you a negative 0.05. Pretty close to 0. 0.65 minus 0.62. When you subtract England from London, your resulting vector is going to retain its capitalness, for lack of a better word. Neither of them are associated with Frenchness, so that is going to stay around 0, and placeness is going to cancel out. Now we're going to add France, right? So France is low on Englishness, so Englishness is going to not move very much. It's going to stay close to 0. France, not tightly coupled with capitalness, so capitalness is going to remain high. It's not going to move much, but it's going to remain high. Now France, being much more French, is going to bring that vector or that magnitude up significantly, and then placeness is going to come right back to 0.4. And what we're left with is negative 0.04, 0.65, 0.8, and 0.4, which is very close in vector space to Paris. In fact, if I were to subtract Paris from this resulting vector, you get 0.05, 0, 0.05, and 0, which is very close in vector space. So that's kind of the example. And that is how you use neural networks to train an embedding such that the resulting vector retains meaning, right? Because it is more closely, because it appears in context with similar words, it's going to be more tightly coupled to certain concepts. And then those couplings become the magnitude of your vector in various dimensions and allow you to perform this vector math so that you can, so that the vectors retain the relations between words. Okay. So that is essentially how embeddings are trained. I did want to mention a couple of other things here before we get into examples. So we talked about word vectors, token vectors. You can create similar vectors for larger pieces of text. You can create sentence vectors, you can create document vectors, and they're all based on word vectors. So to do this, you're going to start with word vectors basically all the time. There's some naive ways to create vectors for larger pieces of text. You can just average the underlying word vectors. You can take the sum of all of them, which is going to result in some big, longer vector. But basically, the endpoint of that vector would define your sentence vector. You can take the weighted average of the underlying vectors. These are all very naive ways of doing it. Most sentence and document vectors nowadays use attention and transformer-based models. They all start with the word vectors that we talked about. The point here is you can take vectors of larger pieces of text. It's all based on word vectors, and the meaning is retained in a similar way. And most of the examples I'm going to talk about later are actually going to be working off sentence or document vectors. Next, there is a problem with word vectors, and that is context. Right? Word vectors know nothing, even though they're trained on the context of words, they don't know anything about the context that the word is currently being used in. So some words, like Apple, mean different things in different contexts. Apple can be the maker of your iPhone. It could be the thing that fell on Newton's head. Riverbank could be the edge of a river. I'm sorry, bank could be the edge of a river, or it could be the place that you store your money. Word vectors don't know anything about this. And this is kind of foreshadowing for our next talk. This is where the attention mechanism comes in. But word vectors in and of themselves don't solve this problem. Okay, so let's talk about some of the practical uses for embeddings. Now that we've gone to all the trouble of training these word vectors, what do we do with them? Well, the first thing is you can use them as inputs to other algorithms, right? It is difficult or impossible to take just text and input it into another algorithm. Typically, algorithms work off of numbers. So you creating these word vectors gives you a nice entry point to using more traditional machine learning algorithms. Right? If you haven't guessed already, large language models take word vectors as inputs. They don't take actual words, they take word vectors, which is why we're on this step of the journey talking about large language models. But you can feed them into more traditional machine learning algorithms as well. So one thing that we've been investigating is, we're a marketplace. We have purchase orders that go back and forth between suppliers and customers. People are always interested in whether or not a purchase order is likely to result in a change order. So we can use machine learning to look at the metadata around these purchase orders and try to predict whether a change order is coming. We can also, people are using our system to talk about these purchase orders as well. We can take the sentence embedding of the various sentences that people have input into the system, and we can correlate the dimensions of the resulting vectors with the ultimate outcome. Did this result in a change order? Did it not result in a change order? And we've found certain dimensions that do correlate with that. So what we can do is next time someone is talking about a purchase order, we can take the embedding, we can look at that dimension that can be fed into our more traditional machine learning algorithm and become one of the inputs that helps us decide whether or not we think a change order is coming. So that was a really interesting use of word vectors and a way of tying it back into machine learning that you might already be doing. Pardon me. One of my favorite use cases for word embeddings is something called semantic search. So we're all familiar with syntactic search, right? So if I search for the word gene editing using syntactic search, what it's going to do is it's going to look for documents that contain the word gene. It's going to look for documents that contain the word editing. Those will all be hits. And if I happen to find a document where those words appear next to each other, that'll be scored higher. Semantic search works a little bit differently. Semantic search takes pieces of text from your document, takes the embedding and stores those vectors. Then when somebody enters a query, you don't necessarily search for the word in the query. You take the embedding of the query. That puts you at a point in meaning space, and then you look for vectors in your database that are close to it. And then you're going to get results that mean something similar to the query, but don't necessarily share the same words. So when we were working on this internally, gene editing was my favorite example, because I searched for gene editing and I immediately got results for CRISPR, which syntactically is not at all similar, but semantically is very similar. And I thought that was a great example of using vector-based search to search by meaning rather than just to search by words. I did say close in meaning space. That can mean a few different things. Obviously, everybody's favorite Euclidean distance, Pythagorean theorem, that extrapolates nicely to however many dimensions. It is computationally intensive. So what people generally do is cosine similarity, which can be done using matrix math, which we'll talk about next time. And basically, this relies on the fact that all of our vectors start at 0, 0. So since they all start at 0, 0, if they're close in space, the angle between them is going to be very small. So doing cosine similarity basically assesses, how small the angle is or how large the angle is between them, and the smaller the angle, the higher the cosine, the more tightly they are, the more tightly related they are. And as you might imagine, our existing databases are not necessarily well tuned for this. So we need new indexes. So there's been a bunch of well, new to me, I don't know, they've probably been around a little while, indexes to support this. Things like local sensitivity hashing, inverted file index, and more recently, hierarchical navigable small world indexes. There is myriad databases coming out that support these indexes, purpose-built for these types of use cases, but there are also plugins to existing databases. So if you're using Postgres, you can use PG Vector to access some of these index types. If you're using Solr or Elasticsearch, some of these indexes are getting built in there. We're not going to go any deeper than that, but just know if you're building an application like this, there are purpose-built databases for this, but you might not need one. You might be able to at least get started with the database that you're already using. Another use case, which is very closely related to semantic search, is I think contextual advertising, right? So you can imagine we are all familiar with buying keywords for advertisements. You go to Google and you buy some keywords. Rather than buying a keyword, you could imagine buying a chunk of meaning space or buying a chunk of vector space. Give me everything that is, closely related to gene editing. And then you're buying CRISPR and gene editing at the same time. And if somebody types in something else with the word gene in it, but doesn't mean the same as gene editing, you're not going to necessarily hit for that. So I'm just trying to provide some ways of thinking about the uses for these vectors. A couple more examples. Retrieval augmented generation. If you're following the LLM space, RAG has been all over the place in the last 6 or 9 months. This is a way of using semantic search or semantic search combined with syntactic search to inject information into prompts, right? So let's say you had a bunch of data that's internal that you wanted to interact with using a large language model. You could use RAG to do that. And what you would do is you would chop up all of your internal data into chunks of text. Maybe it's sentences, maybe it's paragraphs. You would take embeddings of each of those. You'd store those in the database. You would use semantic search or a combination of semantic and syntactic search when someone asks a question, and you would search for text that is related to that question. You would use that text to generate a prompt to your LLM such that when you ask the question to the LLM, the information is right there. So let's look at a quick example. We've had great success doing this with our security policies. So we've taken all of our security policies, built a RAG database from them, and we can use this to help us answer security questions. We get these questionnaires from pharmas that want to know about our security policies. So the question might be, what are scientist.com's password requirements? Now, a base LLM isn't going to know anything about our password requirements, but if we feed this to our RAG database first, the resulting prompt is going to be something like, users must use unique passwords. That's going to be a sentence in our security policy. We use single sign-on where possible. Passwords must be at least 12 characters long. These are all going to be chunks of text that came out of our RAG database, and we're going to prepend that to the prompt. So ultimately, this is what gets sent to the LLM. So the LLM says, what are scientist.com's password requirements? It has the requirements in the prompt, and it can then give a natural language answer. So no sort of fine-tuning or training necessary. You can just feed it the data. That's the retrieval augmented portion of generation. Down to the last 2 examples here. Clustering. I think there's a lot of really interesting use cases for this. So the resulting vectors are going to point in a bunch of different directions. We can apply more traditional machine learning, things like k-means clustering, to try to find clusters of those vectors, a bunch of vectors that are pointing in a similar direction. And this can help us identify topics or themes in our underlying data. So here's an example application. Imagine you go to the preprint server archive, and this is all publicly accessible. You could download all of the papers overnight, or maybe all of the papers for the past week. you could create embeddings of all of the abstracts, or maybe you take the embeddings of all of the entire paper, or maybe you take the embeddings of just the methods section, whatever use case you're targeting. You could then cluster those embeddings, use k-means or some other clustering algorithm. You could take the centroid, like the mean of those resulting clusters, and you could sample the resulting text to see what that cluster is, right? So maybe the cluster is talking about, new novel coronavirus treatments or whatnot. That would end up in a single cluster, and you could inspect the pieces of text in that cluster to see if that topic is trending. More vectors means more interest in that particular time period. And then building off of the clustering, you could then use that to build, to make automated stories or automated newsletters, automated blog posts. I would say drafts. You wouldn't want to hook this directly up to a publish button. But once you had those topics, you could sample the underlying data in a method very similar to retrieval augmented generation. You could feed the resulting text from the trending topics, the trending themes. You could feed that to an LLM and ask it for a draft of a newsletter or a draft of a blog post. And then when you got into work in the morning, you would have a couple of different, potential pieces of content that you would want to look over before using. Okay, so the goal of that was really to just kind of talk about some of the potential uses for word vectors. Now that we've taken natural language, we've embedded it in a vector space and can perform math on it, what can that math do? And hopefully this has been somewhat thought-provoking. And that concludes the presentation portion. Let me find the Q&A tab. Turn my camera back on. We'll see if there are any questions. Okay, first question. In practical terms, how can developers ensure that their embeddings do not inadvertently encode or propagate biases from training data? That is an excellent question. Right? You're going to want to, I think, curate the data that you get. Right? Like, you're not going to want to download all of 4chan and create embeddings off of it. You're not going to have a good time. But so I think you would want to, in general, more text is better, but you're going to want to curate that text to make sure that the text is appropriate for your use case, right? And you can be pretty broad about that, right? Just because you're targeting a scientific application doesn't mean that you can't use Pride and Prejudice in your training data, right? Like, it doesn't have to be science related, but it has to use language in the way that that you're interested in using it. And I would stay away from data sources that have a lot of bias. That said, it is encoding the structure of the way the language is used. So if there's biases in the underlying data, like there will be biases in the resulting embedding. There are probably, I'm sure there's people smarter than me working on that problem. So I'll just say to look out for it and be careful, to carefully curate the data that you're putting in. Next question. What impact do embeddings have on the computational efficiency of language models, especially in large-scale applications? That's a good question. We'll see this more in depth, particularly in the next talk. But the size of the embedding does change the size of the data that's going in, right? So larger embeddings can result in more expensive computations. And what we've seen recently, actually, since I put this together, actually, I've noticed some embedding algorithms that allow the user to dynamically change the number of dimensions. And what that means is basically that the more important dimensions are, well, I shouldn't say that. That's an assumption. But like some of the new embedding algorithms from OpenAI, you can ask OpenAI for embeddings of text and use their algorithms. Some of those allow you to dynamically reduce the dimensionality. So what you'll see is in some of these databases, there'll be hard limits on how many dimensions you can query. So some of OpenAI's older models had a large number of dimensions. I think Da Vinci had like 16,000 dimensions or something like that. That's a lot for a database to handle. So the newer embeddings have fewer dimensions, and the newest embeddings actually allow you to ask for fewer dimensions because computing nearest neighbor and cosine similarity is going to be faster on smaller dimensions. We'll see more about how it affects large language models in subsequent talks. Next question. How do RAGs know which piece of text to send to the LLM? That is a combination of semantic and syntactic search. So you would have to tune it to your liking, but like in my example, we used our security policies to populate our RAG database. So we chopped up the security policies into individual sentences, and some of those sentences say things like passwords must include 12 characters. And when you take the embedding of that, and you take the embedding of what are scientist.com's password requirements, those are going to be near enough in vector space that it's going to find that vector, it's going to know that it's associated with that chunk of text, and it's going to pull that chunk of text out, and that's what will cause us to embed it into the prompt. So basically, yeah, the question is going to appear in meeting space in a similar area as the answers. But it is popular to combine syntactic and semantic search. So you would also search for just pieces of text that match password, for instance. Okay, next question. Could you discuss the significance of dimensionality in word embeddings? How does the choice of dimensions affect model accuracy and training time? That is an excellent question. When I first started this, I kind of naively assumed that more was better, right? If you looked at the first embeddings that came out of OpenAI, their first embedding model that I was aware of was Ada, and then it went to Babbage, then it went to, there was one in the middle, then it went to Da Vinci, and they steadily increased in size. And I think naively, at least I, maybe more broadly, thought that larger embeddings were better. If you look at them more recently, they're coming down in size, right? So I think we've found as an industry that larger embeddings aren't necessarily better. I'm not sure if that is because of what we talked about earlier, computational efficiency, and it's a trade-off of computational time and accuracy, or if you just hit diminishing returns at some point. I don't actually have the answer to that. I would presume that larger embeddings are going to take longer to train, but I don't have data on that either. And this looks like the last question that we have so far. Does the granularity of embeddings impact their effectiveness? For instance, how do character level embeddings compare to word level embeddings in certain applications? I am sure that character level embeddings have a place. I think that most of the all right, there's some assumptions built into my answer here, but I believe most of the embedding algorithms that we're using nowadays are working off of words or somewhat greater than words. Like I've heard that it is not uncommon to encode the trailing space with a word. So if you have a sentence, words that are in the middle of the sentence would encode the trailing space with the word. And that would give the model a little bit more context. It would say this word is being used in the middle of a sentence versus at the end of a sentence. And then sometimes those same models will encode the punctuation with the previous word. So if you had a word with a trailing space, that means that word is being used in the middle of a sentence versus that word with a period after it, which means it's at the end of a sentence, versus that word with an exclamation point after it, which is at the end of a sentence. That means something slightly different. So I think in general, they're moving to, I don't know if I'd say that's less granular or more granular, but they're moving to somewhat, wider tokenization, if that makes sense. But yeah, I think ultimately it depends on your use case, and I would encourage people to try different embedding methods to see what works best for them. I think we actually got through all the questions, and we're basically on time. So let me get back here. Excellent. So I think that brings us to the end. So thank you, everybody. I really appreciate you taking time out of your morning to spend it with us. If you have a moment, please fill out the survey. I would love your feedback on how this went. We do have 2 more sessions. The next one is on July 30th. It's another Tuesday in a couple of weeks, and we're going to talk specifically about attention and how, which is a portion of the transformer model, which is ultimately what all of this is leading up to. And with that, I'm going to end the webinar. Thank you very much.